Imagine dropping a single vibrant drop of ink into a clear glass of water. What happens?
Well, it spreads out.
Yeah.
Slowly, predictably.
Right, diffusing until the water is, uniformly tinted. That's a classic example of something spreading.
Standard diffusion, yeah.
But what if that ink drop, instead of just gently mingling, suddenly, well, exploded outwards, moving far, far faster than you'd ever expect?
Faster and maybe not so predictably.
Exactly. What if it defied our everyday intuition about how things spread?
It sounds a bit like science fiction, maybe. But this kind of accelerated non-linear spreading is very real.
It is.
And it's actually a fundamental part of how many natural systems behave.
Absolutely. Welcome to the Deep Dive. Today we're plunging into a truly fascinating concept that, really challenges our everyday understanding of movement. Superdiffusion and turbulent transport.
And this isn't just about things spreading quickly, is it?
No, not at all. It's about a surprising non-linear relationship between how far something moves and the time it takes to get there.
Right. So our mission today, really, is to uncover what superdiffusion truly is.
How it radically differs from that simple, predictable spread of normal diffusion we just talked about.
Mm-hmm. And also its surprising presence, in everything from the tiniest components within our cells.
All the way up to the vast, turbulent expanses of the cosmos.
Exactly.
And we'll also touch on the cutting-edge mathematical breakthroughs that are finally giving us a rigorous understanding of these phenomena.
And their profound real-world implications, of course.
It's a topic that brings together history, advanced mathematics, cosmic mysteries, all in one beautiful, complex package. I'm genuinely excited to see how all these pieces connect in this deep dive.
Me too. So to grasp superdiffusion, like you said, we first need to establish our baseline. Normal diffusion.
Okay.
Think of something like Brownian motion, the jittery movement of pollen grains in water, famously described by Albert Einstein and Marian Smoluchowski.
Right, the random walk.
Precisely. For a particle undergoing this kind of motion, the average distance it travels, squared, the mean squared displacement, or MSD, is directly proportional to time.
So linear.
Linear. Imagine you wait twice as long. On average, the particle will have covered twice the square distance. It's a steady linear progression.
Okay, so that's the predictable linear march. But if that's normal, how does anomalous diffusion break that rule?
Well, anomalous diffusion basically throws that linearity out the window.
Yeah.
Instead, the average square distance follows a power law. It's proportional to time raised to some exponent, which we usually call alpha.
Alpha.
And this alpha value is the key. It tells us exactly what kind of spreading we're looking at.
Right. So how does this alpha value help us classify these different types of movement? What are the categories?
We can classify diffusion based on this exponent alpha. It essentially defines whether something is moving slower, faster, or exactly like normal diffusion.
Okay.
So if alpha is less than 1, we have subdiffusion. This means movement is actually slower than normal.
Slower, like getting stuck.
Kind of. Picture a random walker trying to navigate a hopelessly crowded room, constantly bumping into people.
Okay, I can see that.
Or think about inside our cells how proteins diffuse. They're constantly hindered by other molecules or cellular structures. Their progress is impeded.
Makes sense. So that's alpha less than 1.
Then, when alpha equals 1, that's our baseline, Brownian motion, the steady linear spread.
The normal case.
The normal case. Now, for the star of our deep dive, superdiffusion. This is where alpha is between 1 and 2.
Right.
This is when particles spread faster than normal diffusion, like they're taking exceptionally long, infrequent jumps, maybe, or being actively propelled somehow.
So they're rocketing ahead of what simple random walks would predict.
Exactly. Then, if alpha actually equals 2, we're talking ballistic motion.
Ballistic, like a straight line.
Pretty much. A particle moving in a straight line at a constant velocity. No randomness, just pure directed movement. Think of a bullet fired from a gun.
Got it.
And then there's even hyperballistic diffusion, where alpha is greater than 2.
Whoa, faster than ballistic. How does that work?
It's pretty exotic. It's been observed in some optical systems where the spread of light somehow accelerates beyond even a simple straight path. It's almost as if it anticipates its destination in a way.
That's fascinating. So we're really focusing today on that superdiffusion range, alpha between 1 and 2, where things just take off faster than we'd normally expect.
That's the core, yes.
But this sounds quite theoretical, maybe. Where do we actually see this superdiffusion happening in the real world? Is it just a lab curiosity or...
Oh, far from it. It's surprisingly ubiquitous. It shows up in the most unexpected places.
Really? Like where?
Well, actually, one of the earliest and most profound observations of superdiffusion takes us back almost a century, to 1926.
Okay.
There was a Quaker scientist named Lewis Fry Richardson. He's known for his pioneering work in numerical weather prediction, trying to forecast weather using math.
Richardson, right.
He was studying turbulent weather, and he stumbled upon this peculiar piece of data, a tabulation of landing spots from a Paris gas balloon race that had happened nearly 2 decades earlier.
A balloon race.
Yeah, and he combined that data with his own careful observations of things like volcanic ash trajectories and even the flight paths of dandelion seeds carried on the wind.
Weather balloons and dandelion seeds. That sounds like a wonderfully, almost quaint origin story for such a complex scientific idea.
It really does.
It makes you wonder what other profound insights are just hidden in plain sight, waiting for someone with that kind of curiosity.
Absolutely. And what Richardson found was groundbreaking. He demonstrated that the Earth's atmosphere exhibits superdiffusion.
So the air itself spreads things out faster than expected.
Yes, the turbulent swirling at both large and small scales scattered objects, the balloons, the ash, the seeds, with astonishing efficiency, much faster than simple, predictable diffusion would ever suggest.
Wow.
This was a critical early observation of this very phenomenon. It hinted at a kind of hidden order within the chaos of turbulence.
Okay, so from atmospheric movements, which are huge, where else are we seeing this super fast spreading? Does it scale down or up?
Oh, it absolutely scales. It pops up in incredibly diverse natural phenomena.
Whoa.
Within living cells, for instance, we see structures like telomeres.
The caps on our chromosomes.
Exactly, the protective caps in the nucleus, or ion channels and plasma membranes, and even colloidal particles suspended in the cytoplasm. They all exhibit super diffusive behavior.
So their movements aren't just random jiggling.
No, they seem to be faster, more exploratory. Beyond biology, it's been observed in ultra-cold atoms, in harmonic spring mass systems, even in something as seemingly mundane as moisture transport within cement-based materials.
Cement? Really?
Really. And then if we zoom way out to the cosmic scale, it's crucial for understanding how different elements mix in the vast interstellar medium, the space between stars.
That's incredible.
What's truly remarkable is how scale-independent this phenomenon appears to be.
It really is wild to think that something governing how telomeres move in our cells could be related somehow to how cosmic dust spreads across the galaxy.
Mm-hmm.
This raises an important point, though. You mentioned turbulence earlier, and that's a concept that's usually described as notoriously difficult to understand, right?
Oh, absolutely.
So how does superdiffusion fit into that picture of chaotic movement?
Turbulence. Yes. It's often called the last great unsolved problem of classical physics, precisely because it is so difficult.
Why is it so hard?
Well, while we have these beautiful equations like the Navier-Stokes equations that describe smooth laminar fluid flow, turbulent flow is different. It has these unpredictable, self-similar eddies and whirlpools interacting across all sorts of scales.
Self-similar, like fractals.
Exactly like fractals in a sense. This makes precise predictions incredibly difficult, even impossible in many practical cases. It's actually part of one of the Millennium Prize problems in mathematics.
One of the million-dollar problems.
That's the one. A set of 7 challenges where solving just one gets you $1 million. That's how hard understanding turbulence fully is.
So it's basically organized chaos that's largely beyond our current mathematical grasp. But it's humbling, really.
In many ways, yes. But Richardson, back then, with his profound intuition, had a powerful analogy for it.
What was that?
He hypothesized that if you drop 2 rubber ducks, as he put it, into a turbulent river,
Okay.
they won't just drift apart slowly and predictably. They'll actually be carried apart much faster than expected, thanks to all the swirling currents acting on different scales.
So the turbulence itself actively pushes them apart faster.
Precisely. That boosted scattering, where particles accelerate their spread due to the underlying chaotic flow, is a hallmark of turbulence. It's exactly superdiffusion at play.
Okay, this is where it gets really interesting for me. I heard about a recent breakthrough in finally proving this superdiffusion mathematically in a turbulent setting. What was the understanding before this? Was it more hand-wavy?
Yes, this is huge news. Just last year, 3 mathematicians, Scott Armstrong, Tuomo Kusi, and Ahmed Bourabi, managed something remarkable. For the very first time, they rigorously proved superdiffusion in a simplified turbulent fluid model.
Simplified, but still turbulent.
Yes. For decades, physicists had used a technique called renormalization to estimate the superdiffusion rate in these kinds of models.
Renormalization, I've heard of that in particle physics.
Right, and while renormalization often yielded the correct answers, it lacked strict mathematical rigor. Richard Feynman famously called it hocus pocus.
Hocus pocus, wow.
Because, well, mathematically it wasn't fully justified even if it worked. This new proof by Armstrong, Kusi, and Bo-Rabi provides that solid mathematical footing. They used an arcane but powerful technique called homogenization.
Homogenization, that sounds complex. Can you give us an intuitive sense of what that means here?
I'll try. Homogenization essentially allows them to average out the chaotic, small-scale variations within the turbulent flow.
Like smoothing out the noise.
Exactly. To reveal the underlying large-scale patterns and behaviors. It's like looking at a highly detailed, noisy image and then blurring it just enough to see the big picture, the dominant trends emerging from the chaos.
That makes sense.
But it was an immense effort, over 300 pages of calculation apparently, nearly 2 years of work. And they had to overcome widespread skepticism that such an approach was even possible for this problem.
That's right.
Yeah. Unlike a straight highway, these cosmic magnetic pathways aren't straight. They diverge and twist and turn as you follow them because of the turbulence.
So the magnetic highway itself isn't straight, and that leads to unexpected detours for the cosmic rays, making them spread faster.
Precisely. If cosmic rays are freely streaming, meaning they experience minimal scattering, they just follow the field lines. Their displacement perpendicular to the average magnetic field direction increases significantly faster than normal diffusion.
How much faster?
It scales like time raised to the power of 3/2, T32. Much, much faster than linear T1.
Oh.
This is directly linked to the magnetic field line wandering theory developed by Lazarian and Vishniac back in 1999. And you can hear the echo of Richardson's work from decades earlier.
That Richardson diffusion again.
Mm-hmm. Now, even if there's efficient scattering, if the cosmic rays don't just follow the lines but get knocked around a lot, their diffusion across the average field is still super diffusive.
Still faster than normal.
Yes, but at a slightly slower, though still accelerated, rate, proportional to time raised to the power of 3/4, T34. Both cases, T32 and T34, are significantly faster than normal diffusion, which is T1.
Okay. And what about the actual nature of the turbulence in space? I understand there are different modes or types of waves involved.
That's correct. We're often talking about magnetohydrodynamic turbulence, or MHD turbulence. That's how electrically charged fluids, like the plasma in space, churn and swirl of the influence of magnetic fields.
MHD, right.
And this MHD turbulence is composed of different fundamental modes or types of waves: alphanic modes, fast modes, and slow modes.
And do they affect the cosmic rays differently?
They do. What's fascinating is that the alphanic modes seem to be the primary drivers of that magnetic field wandering we talked about.
So they cause the T32 superdiffusion.
Largely, yes. The fast mode, however, is thought to be crucial for scattering the cosmic rays, for knocking them off the field lines.
Ah, so one mode makes the paths wander, another mode kicks the particles off the paths.
In simple terms, yes. And the effectiveness of this fast mode scattering depends on various factors.
Like what?
Like its energy fraction compared to the other modes. This varies with things like the sonic Mach number, how fast the plasma is moving compared to the sound speed in it, and the alphanic Mach number, how fast it's moving compared to the speed of these alphin waves.
Okay, so the overall speed and magnetization matter.
They do. And these factors directly influence how easily cosmic rays get scattered, which, in turn, impacts the cosmic rays' mean free path.
Their average travel distance between scattering.
Exactly. The average distance they travel before something, like a magnetic field fluctuation associated with the fast mode, knocks them off course.
So understanding these different modes and how they interact is absolutely vital for predicting cosmic ray behavior across the universe, for understanding where they come from and how they get to us.
Absolutely. These findings are vital. For instance, for understanding how cosmic rays get accelerated to incredible energies in extreme environments, like supernova remnant shocks. And also for explaining observed phenomena like suppressed diffusion in certain regions, like supersonic molecular clouds, where we see cosmic rays seemingly having a harder time penetrating.
Because the turbulence properties are different there.
Potentially, yes. The scattering might be much more efficient, or the field line wandering different. We're also uncovering other new effects predicted by these theories.
Such as?
Things like suppressed retracing of cosmic rays, meaning they're less likely to double back along their path than previously thought. and something called mirror diffusion.
Near diffusion.
Yeah, where cosmic rays don't necessarily get trapped in magnetic bottlenecks, but might actually bounce off magnetic compressions, almost like hitting a magnetic mirror that reflects and redirects their path.
It's incredible how turbulence, something that seems so chaotic, introduces these specific, powerful patterns of movement. It's not just random. There's an underlying complex physics dictating the spread.
That's the beauty of it, yes.
So we've explored how external forces like turbulence can drive superdiffusion across vast scales. But what if the material itself, or maybe its concentration, changes the very rules of spreading?
Ah, yes. Nonlinear diffusion.
What if the diffusion process isn't just fast, but truly explosive?
Well, explosive in a scientific sense, perhaps.
Yeah.
This can happen when the diffusivity itself isn't a constant number,
Okay.
but instead it depends on the particle concentration. So as the concentration changes locally, the rate at which things spread from that location also changes dynamically.
So if you have a dense clump of something, it might spread differently than if it's very sparse, like it pushes itself apart faster if it's crowded.
Precisely that kind of idea. Solutions to these types of nonlinear diffusion equations can exhibit hyperballistic diffusion.
Hyperballistic again. Alpha greater than 2.
Yes. Meaning the displacement grows even faster than simple ballistic motion, alpha 2. What's particularly interesting is that in multidimensional systems like 2D or 3D, the world we live in, this hyperballistic diffusion, becomes possible, even when considering relatively simple particle interactions.
Under what conditions?
Especially in cases where particle velocities or maybe the lengths of their jumps diverge, they get infinitely large as the concentration approaches zero.
So particles on the very edge of a cloud move extremely fast.
That's one way to think about it, leading to incredibly rapid expansion of the boundary.
And this leads to what you called explosive decay. What does that mean for how an initial concentration profile dissipates? That sounds dramatic.
It means an explosive decay, mathematically speaking, of initial concentration profiles. The spread is qualitatively faster than even normal diffusion or standard superdiffusion.
Can you give an example?
Imagine maybe a contaminant spill that instead of slowly fading over days or weeks, practically vanishes in a blink because the edges spread out so incredibly fast. Or perhaps a chemical reaction front that suddenly snaps across a medium after a long period of slow activity.
Wow.
That's the idea behind explosive decay. It means systems can clear themselves out or transition with astonishing, almost instantaneous efficiency, really defying our usual intuition about how long things should persist or take to spread.
So to recap this incredible deep dive then, we've gone from a simple drop of ink to the vastness of space. And we've discovered that superdiffusion and turbulent transport are far more prevalent and frankly more complex than traditional diffusion models might suggest.
They appear across essentially all scales of the natural world.
From the chaotic dance of molecules in our cells,
To the turbulent flows of cosmic rays across galactic distances.
and they fundamentally reshape how we understand dispersal and mixing.
Absolutely. And what's truly fascinating, I think, is how this journey has brought together these different threads. Historical observations like Richardson's,
Cutting-edge mathematics, like the recent proof.
complex fluid dynamics, astrophysical phenomena, all linked by these surprising nonlinear power laws of anomalous diffusion,
It really underscores that the universe is full of these unexpected behaviors.
where chaos, perhaps counterintuitively, often gives rise to stunningly efficient processes.
It really does. Which leaves us with an important question for you, the listener, to ponder. From the microscopic dance of molecules within our cells to the vast turbulent flows of cosmic rays across the galaxy, understanding these anomalous movements isn't just about solving equations, is it?
No, it's about fundamentally reshaping our understanding of how chaos, surprisingly, can bring a kind of order, or at least predictable patterns, to the universe.
So the question is, what other anomalous phenomena might be hiding in plain sight, just waiting for us to uncover their true nature and the hidden rules they follow?